In this video, we're going to cover the test bench for Blinky with an APB interface. Stolen heavily from the Blinky test bench. So I'll just talk about the changes from that test bench. Here we added all of these signals here. Like all the regs are driven from the test bench into the Blinky block. The Blinky block returns the wires, which is P ready and PR data. And so that's new signals that are getting defined. The clock stayed the same, of which it's a 100 megahertz clock. It toggles every 5 time units. And in this case, the time unit is 1 nanosecond. So the clock is toggling every 5 nanoseconds for a period of 10 nanoseconds, which is 100 megahertz. So that creates the system clock. Then we instantiate the Blinky block. I think in the previous design, we decided we wanted to call it U Blinky. So let's just do that. INKY. So we instantiate the Blinky block and we define extra inputs and outputs where it's a dot, the internal signal, and then in parentheses, the external signal. So this is a named port mapping. You can also have an ordered port mapping, but as you can see, when you start adding more and more signals, it's harder and harder to keep an order correct. So almost always you'll see a named port naming convention. So here we've added two tasks. We've added an APB write task and an APB read task. And a task you can view as kind of like a procedure or a function and takes a couple of parameters into it. So in this case, it takes in the address. So we might do a write and we'll write to many different addresses with many different values. So I called it iAddress for one input and IW data for write data. And then we implement this protocol for an APB write. And similarly for the read, we take in the address and what in this case we expected, and we'll do some testing down here to see that we actually got when we do a read back. We got what we expected. So we'll talk about that in a little bit later. Let's go blast through and finish the test bench first. So we have these tasks, then we have the main initial block, which is you can view it as your main program. And in this, we define some variables, no change there from the previous one. It's an initial block, which means it just gets run once, as opposed to up here where it's an always block, which means that with an always block, and I think it runs till completion and then it repeats again. And so with initial block, it just runs once. So I guess that's more like a normal procedure. And let's see, is that it just runs once. It runs all the way down. Um, and in this case, the only difference is that at the beginning of the test, we do an APB read of address, this address here, and of which we're particularly only interested in this 04, which is address 4. And we read it and we check and we want it to be 128, which is what we know is the reset value. And so it'll compare, well, it'll compare that and see that it's correct. And then we do an APB write, and we write to address 4 with this new value blink rate, which we called 300. So we write into a 299, and then we read it back and we see that we got 299. And then after that, we've set the blink rate, and then we go into a big long loop, a for loop, wait 10,000 times. It'll blink many times during that time. And this test bench will look for it to make sure it blinks at the right time. And there's the right time duration between from one blink to the next blink. And if it's not, it'll print a fail. Otherwise, it prints a pass. If anything ever fails, then at the end of the test, it'll print failed and it'll tell how many times something failed. Otherwise, we'll say, hey, print passed. And that's it. And this is, just view this. If you ever want to turn on waves, just pop this code at the very end. This is the name of the file, the waveform file. VCD is the format. It's like something like change description. I don't know. Value change dump, I think maybe is what it stands for. Um, but anyway, just you can just pick any name you want to. I picked test.vcd. This dump vars tells what level of hierarchy you want. Essentially, this part here makes it so you dump every signal that's in the design. That's almost always good enough. Sometimes if you have huge simulations or huge designs, you might want to pick and choose what you dump. But for almost anything you do for a long time, he'll be just dump everything. Just copy this into your test bench if you ever want to get waves. Um, yeah, so now let's go back to the tasks. So in this case, what we want to do is we want to emulate this. We want to basically create this, right? And so, slow down, slow down. So we want to have the select. So for a read operation, let's take a look at that first. We want to pulse select for 2 clock cycles. We want to keep write low. We want to put an address on there for stable for 2 clock cycles. We don't care about write data, so we maybe drive that low. We want enable to be low for the first clock cycle and high for the second clock cycle. And for the read data, we want the data to be valid whenever this enable is here. We want that data to be valid. So it's valid here, and that's what's driven back from the Blinky plot. And this actual is, I'll show you what I did in the test bench for that. Um, then the P ready, you can see it's always high. And so that's what we're trying to emulate in this test bench. And when this test bench, what it's doing, the reason, right, is what it's actually emulating is like an ARM processor or RISC-V processor that performs this operation whenever it wants to read or write from the FPGA logic, fabric, the gateware. So anyway, so here, like on the APB read, is that we have, right? So I instead of like a 2 clock cycle, I made it a 4 clock cycle where everything is low for the first and fourth clock cycles, just to basically initialize everything before we start and clean it all up. Kind of wastes a couple cycles, but that's fine. So the first action cycle is here, where we drive the address, we drive cell, we drive write low, and we drive write data low. Boom, wait for a clock cycle. Drive P enable to a 1, wait for a clock cycle, then turn everything off. That's the 2 clock cycle read. And what I've done is right here on the second one here, boom, after the second read, I grab what's on the P-rated our data bus. I grab that and I store that internally in actual. And that's just so I can have a signal that's floating around that I can use later on for whatever I happen to want to use it for. In this case, I go and I compare P actual with the expected value that I passed into it. And if they're not the same, then I bump the fail count and I print a fail message. Otherwise, I just print a pass message. Yeah, so that's essentially what the read transactor is doing. Again, I'm emulating the processor's read operation. The write is very similar in that I have like 2 dummy clock cycles at the beginning and the end to zero everything out, make sure it's stable before and after this operation. And then on the second clock cycle here, I drive the address to the value coming in that I want, the P address. I drive the select to a 1. I drive a write to a 1. I drive the write data bus to the new data value that I want. And then I hold it stable. I drive P enable high for 1 clock cycle. Then I drive it low. Well, that emulates and that creates this scenario where these guys are stable for 2 clock cycles. Enable goes for 1 cycle. And that is how the test bench works. That's it.